Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We are delivering a series of AS and A-level chemistry lecture series. This is the 32nd lecture on organic chemistry 7. And this lecture will complete the paper 1 and paper 2 of AS level. And we will probably continue the third paper also today. Well, now we have been talking about a homologous series of alcohol, and now we will see how it reacts that means how oxidation takes place, reduction takes place with the alcohol series, homologous series. Okay, primary and secondary alcohol can be oxidized by an oxidizing agent, for example, potassium dichromate, which is acidified with sulfuric acid. But tertiary alcohol cannot be oxidized with this reagent. Okay, how do you see that we really oxidize it? The orange color solution of potassium dichromate, which is act as an oxidizing agent. The dichromate 7 ions behave as an oxidizing agent. These ions themselves are reduced. You know that we discussed about redox reaction. If an ion is oxidized, the other ion in the reaction will be reduced. That is why that is the principle of oxidation reduction reaction. So dichromate ion itself, chromate ion itself will be reduced. And that is a green solution. Chromate ion has a green solution. This reaction takes place only if we warm the solution, otherwise it will not. The product distinguished between primary, secondary, and tertiary alcohols with this potassium dichromate solution. In tertiary alcohol, the potassium dichromate solution remains unchanged even if we warm, so therefore there is no reaction. And in secondary alcohol, such as propanol 2, will be oxidized to a ketone. Here it is. Secondary alcohol, it oxidizes to ketone. And in primary alcohol, it oxidizes to ethanol. Okay, now ethanol can also be oxidized further to ethanoic acid. As an ethanol is further oxidized with ethanoic acid. Well, what about carboxylic acid? What we know about carboxylic acid? We said that we can oxidize alcohol to aldehydes, and further oxidation it does carboxylic acid. That's what we already discussed. And then you see that we can also form carboxylic acid from another compound, this nitriles, and here is the nitriles, this functional group of nitriles is this one. And when we replace this with hydrofluoric acid, the hydrolysis occurs, and in alkyl groups, it is converted to carboxylic acid, transforming the carboxylic acid. Okay, what about carboxylic acid? Is it a weak acid or base? Yes, it is a weak acid because it does not dissociate completely when added to water. But it, however, dissociates a little bit. There is the dissociation of carboxylic acid. We have ethanoate ion and proton and aqueous media. And this equilibrium shift towards left, and therefore there is a less number of hydrogen ion when we dissociate it, and therefore it is the pH of this solution will be less than 7, and hence ethanoic acid form an aqueous solution, ethanoid iron water. This is what the reaction goes. Well, as it is acidic, so you can see that it reacts with the usual reaction of acids. What do you mean by usual reaction of acid? When we react this with alkali, what happens then? We get sodium ethanoate and water. When it we react it naturally, we get a salt, or let's say this is ethanoic acid, and then we react with magnesium, and we get salt of magnesium plus hydrogen atom. We know carbonates also dissociates when reacted with acid and form salt, water, and carbon dioxide gas. So here the ethanoic acid, carbonate, and we get salt of potassium and water, carbon dioxide. Okay, then we go for next slide, and we are coming to another homologous series of organic compounds, and we call it aldehydes and ketones, the classes of carbonyl compounds, and the functional group is this. Okay, aldehydes can be formed, or aldehyde can be formed by oxidation of primary alcohols. Ketone can be formed by oxidation of secondary alcohol. What happens? Now, naming of these aldehyde and ketones, we have to remember that whenever it is aldehyde, which form from primary alcohols, we have the chain of a carbon atom. The last carbon atom is bonded with this functional group with the hydrogen atom. That's why it is the end of carbon chain where we have this functional group and hydrogen. So here it is. You see, this is functional group of aldehyde, functional group of aldehyde, functional group of aldehyde, functional group of aldehyde, and aldehyde. We call it methanol, ethanol, propanol, butanol, pentanol. So here we don't, we see that every functional group is in the last carbon and series of carbon, last carbon. Yeah. And this is how we give naming of this. We have aldehydes derived from the name of the equivalent alkane. So E, last word E, is then converted to L. So methane, then methanol, and similarly ethane, ethanol. So from alkane, we are getting the structural formula and the aldehyde. Similarly, if we go for ketone, we see propanone, we call it propanone, butanone. And then now the numbering, you have to see carefully. Numbering, we are not saying pentanone, we are saying pentanone, because where it is, where is the functional group? You see, up to this, from propanone to butanone, we do not have any choice of functional group. Functional group can be here. And here we go to pentanone and storm. So we see that we can have the functional group in pentan 2, here it is, and then functional group here is pentan 3. So which carbon it is in pentan 3. And that's why here we have the numbering, but in this case of aldehyde, we do not have a number because N carbon having the functional group. Okay, now we go to next. You see, it's a green cheese, blue cheese. A compound of organic compound in this blue cheese, which smell, for which we get the smell, and it is heptane 2-on, heptanone. This is a ketone, heptane 2-on, which is responsible for the smell of the blue cheese. Okay, we go for aldehyde. You see, this is benzaldehyde. This is benzaldehyde. Benzaldehyde is responsible for contributing flavors of many fruits and nuts. So we have the structure, and then we go for the preparation of aldehydes, how we prepare in laboratory. That's we are preparing ethanol. So what we call them? We take ethanol, the primary alcohol, and acidified with potassium dichromate solution, and we gently heat this, what it is, the chips or not, so that anti-bumping agent, and then we reflux it, and then we get ethanol. So here is the reaction for ethanol. We can propanol. We can take an example: primary alcohol, propanol, propan 1-ol. This is a primary alcohol. And we have oxidizing agent. We show the oxidizing agent like this, but you remember we have been talking that potassium dichromate in acidic media behaves as oxidizing agent, and we get propanol and aldehyde. Similarly for ketone, remember that we have to have secondary alcohol, and this is a secondary alcohol because it's attached in this carbon. Secondary alcohol, and we call it propan 2-ol. And it's oxidized, and it is a propanol, a ketone in water. We have been talking about this, and what is this? When we react this oxidizing agent, that means acidified potassium dichromate, the reaction mixture in the flask will change from orange to green. When it is complete, if we take here, it comes up with, first it will be orange color, and then after reaction it will be green color. And therefore, okay, so reduction of aldehyde in alcohol, ketone, reduction of aldehyde in ketone. And we do remember that in organic chemistry, we do use sodium borohydrate or lithium aluminium hydrate as a reducing agent. Sodium borohydrate is a more powerful reducing agent, and then that lithium aluminium borohydrate. Okay, so here we take ethanol, the aldehyde, and then reduce it, and we get ethanol, that is alcohol. And similarly, we take propanol, and we reduce it, and we get propan 2-ol, that is alcohol. It's a primary alcohol, it's a secondary alcohol. So in laboratory, we can distinguish between aldehydes and ketones. And that in that case, we either use Fehling solution or Benedict solution to distinguish between aldehydes and ketones. You see, what is Fehling solution then? It's mixed between one solution of copper 2 sulfate in water, the other solution when we mix to it 2,3 dihydroxy butanediol, that is a tartarate, a solution of tartarate and a solution of copper 2 sulfate mixed in water, and then we call it Fehling solution. When we want to distinguish between aldehyde and ketones with Fehling solution, we have to remember that we have to prepare fresh Fehling solution to distinguish it in the laboratory. Fresh Fehling solution. We cannot have prepared old Fehling solution, which is not stable, and therefore we don't use it. So if we take this, this is let's say this is an aldehyde solution, and then this is an aldehyde solution, and we put Fehling solution in it, and then you see the change. What happens? The Fehling reagent is used to test for aldehyde. Reagent has a blue color, and then it contains copper 2 ions. The test tube in the middle contains Fehling solution, has reduced the aldehyde to form an orange-brown precipitate of copper 1 oxide, which is which cannot be done by ketones. So here is the distinction between aldehydes and ketones. Well, up to that, we were discussing, that means the 32nd lecture, part of the 32nd lecture completes from 1 to 37, completes the paper 1 and paper 2 syllabus of AS syllabus, chemistry syllabus. Now we are going to discuss about third paper, that's analysis, or we call analytical techniques as in syllabus written. So we will discuss this. You know that knowledge of chemistry should be corroborated with an analytical work. That means both quantitative and qualitative chemical analysis is very much needed to learn chemistry in the lab. So laboratory practice is a must for that. In chemical analysis, different chemicals and glasswares are needed to perform the analysis. Chemical analysis are rather cheap, but one thing is that we have to very careful about green chemistry so that we don't, after the reaction, the reagent we take and the sample to be analyzed, we mix together, and then this is no longer usable. We have to throw it out. So we have to be very careful when we are throwing this product. So, but then in chemistry, we do also use instrumental techniques for analysis, which is though expensive, but more, I'll call more green chemistry, and we do not need to be worried about pollution. So moreover, the instrument analysis needs a very small amount of sample, and this sample is not destroyed while we are analyzing it. That is the advantage, but you have to remember instrumental analysis is more expensive, and it needs skilled technical personnel to maintain instruments so that we can use it properly. So now we are in this syllabus, we have to talk about mass spectrophotometer and infrared spectroscopy. So we start with mass spectrophotometer. In earlier lecture, I said, I believe in lecture number 2 or 3, we were talking about mass spectrophotometer, where we detect with the mass spectrophotometer different isotopes of elements and naturally occurring elements. We showed it how mass spectrophotometer works, etc. So, but mass spectrometer is also used very oftenly to identify the unknown compounds, specifically organic compounds, its molecular structure, relative atomic masses, etc. We can find, we can use mass spectrometer, and this is extremely sensitive and requires very small amount. Even very small amount means we can use nanogram, that is 10 to the power minus 9 gram. What happens in mass spectrophotometer? We maintain a high vacuum inside the mass spectrophotometer so that the possible to produce and study ionized molecules and fragments of molecules. These molecular fragments could only exist in high vacuum. So do remember that we need high vacuum in mass spectrophotometer. How it works? We have a sample then, molecular sample, here it is. A high energy electron comes, not a electron from this molecular ion and form a molecular ion, cation, and we will then find out its relative atomic mass, molecular mass, and then fragmentation. Here is the ionized molecule, M1, M2, and then we ionize it. So let's say we ionize the M2 molecules, and then we can fragment it from M1, M2, etc. So if it is not charged, positively charged, we cannot detect it by mass spectrophotometer. So there it's positively charged, we detect it. Uncharged molecule, the fragment molecule, we don't detect in mass spectrophotometer. What we need a high energy beam of high energy electrons, which will bombard the molecules, and this turns them into ions by knocking out one or more electrons. This is what is the bombarding molecules with high energy electrons not only ionizes them but also split them into fragments. That's what we say, splits them into fragmentation. And that fragmentation we use in our analysis. Molecules break up more readily at weak bonds and at bonds which gives rise to more stable fragments. It turns out that positive ions on the change on a secondary or tertiary carbon atoms are more stable than ions on the primary carbon atoms. So such as this species is more stable, this species is more stable, and where a bond breaks and adjacent to the carbonyl compound, a bond breaks and double bond. After ionization, the fragments, the charge species are accelerated and deflected by electric and magnetic fields. The extent of the deflection depends on the mass to charge ratio, what we call M/Z. Is number of charges could be 1, 2, and so on, but specifically let's say in the AS level, practical, we restrict ourselves with J is equal to 1, that is, charge is equal to 1. Okay, here are some spectrum of let's say bromoethane spectrum of mass spectrum of compound bromoethane, and we have a molecular mass. That means when the parent atom is charged, we call that molecular mass charge or molecular M plus, that we call them M plus. So in the left, it is bromoethane. It shows molecular ion M/Z at 108 and 110. Why? Because bromine has got two isotopes, naturally occurring two isotopes. One is 79 and another is 81. So if we take bromomethane, we do have two naturally occurring isotopes of bromine, and thereby one has a charge of 81 and another is charge of 79. And if we calculate the mass of this, relative mass of this, it comes out to be 110. And if it's calculate this mass, it comes out to 108. And you see, here is the peak for 110 and 108. And these raised to what we are calling, it's a fragmented ions. So it could fragment like this. Bromine could be out, loss of bromine gives us this fragment, and then we can lose another hydrogen and we get this fragment, and also another hydrogen, we get this fragment, and these are the fragmented ions peak. So with this, we can see that the molecular mass spectrum of bromomethane, we can find out the mass spectrum and find out how the fragmentation occurs and reactions states in the molecular, as well as we can find out the functional group also in this fragmentation process. In these slides, we are showing two problems. One is problem 1 here, and the other problem 2 here. So we will discuss it in the next class, as well as and details of infrared spectrophotometer and how the infrared spectrophotometer work and how we use it to identify the functional group. Thank you very much for this lecture. We will be coming with 33rd lecture of analytical techniques note. Thank you very much.